Okay, this is one of 6 to 8 problems that our book has. It's really much more of a pre-calculus question than a calculus question, which brings up the point that pre-calculus is, for the most part, harder than calculus. Well, they ask us to graph it, and that once we have the graph, we should be able to answer the question, is it continuous or not continuous, and where. We should be able to answer the question, is it differentiable or not differentiable, and where. But the important thing is to get the graph. Now, this is a piecewise defined function, so I only need to graph each piece and then try to see how they fit together, but we'll do this. How do I graph this first part? Well, I have to know what kind of function it is, and I can help a little bit by pulling out the constants. So let's pull out the constants. I pull out a big G, I pull out an M, I pull out a big R cubed, and all that's left is a little r. Now you should pause it for a minute and ask yourself what kind of function that is. Welcome back. If you paused it and asked what kind of function that is, you should have said linear, because this is just a constant times a variable. In fact, you can actually see that this looks like mx plus b, where b is 0. So not only is it a linear function, it's a linear function that goes through the origin. When I look at the next piece, I'm going to pull out the constants again. And this is a common thing that we do in calculus, where we pull off the numbers off the top and leave what's left like that. So I pull out the G, I pull out the M, what's left is 1 over r squared. You should pause it again and ask what kind of function this is. If you paused it, you should have said, this is one of our power functions from our zoo. In fact, when we graph this, I usually like to call that a volcano. Now, this isn't the whole volcano, it's just a piece of it. And we want to know, how much do I draw of this line, and then stop, and then how much do I draw of the volcano, and continue, and how do they hook up? And I will walk you, I think, to the brink and let you finish it. Now, the very beginning, we're supposed to draw a line, so I'm just going to draw a little tiny thing here, where this is little r, this is our function little g, and we're supposed to draw the line until we get to the radius of the Earth, and then we're supposed to have a hole. So that's the first piece. The second piece, this is still little r, this is still little g. Now I'm supposed to draw the volcano. The volcano goes way up over here, that's not relevant. It comes down here like this, that's relevant only to the point where it actually starts. So what I'm going to do is I'm going to put an R like here. The volcano comes down like this, hits, and then continues down and has an asymptote over here. Now the question is, how does this hook up to this? I don't want to automatically show they hook up or assume they hook up. We should at least talk about it. So there's little r, there's little g, here's our piece of line. There's 3 things that can happen, and in nature, by the way, these things happen a lot, so you don't want to just assume, right? So what's going to happen is, it could start too high and come down like this. It could exactly hook up and go down like this, or it could go down low like this and go like this. Now in nature, all 3 things happen. I want to discuss just commonsensically what might happen. Now, what is this line here? This says start at the center of the Earth, and you're feeling more and more gravity until you get to the surface, and the surface was at big R. Now, what would the top one say? The top one says that if you even walk 1 inch above the surface of the Earth, bam, you feel double the gravity. Well, that's crap. It is just not true that you feel a lot more gravity if you're 1 inch above the surface. So I'm thinking that one, common sense wise, isn't true. This is just common sense, but math is supposed to build on common sense, not replace it. What's the next one on the bottom say? That says you're walking from the center of the Earth, you get to the surface of the Earth, you feel this much gravity, and if you even go 1 inch above the surface of the Earth, bam, you feel half the gravity. Well, that's also crap, right? It just shouldn't do this. Common sense says it shouldn't do that. Now, that's not what the formulas might say. The formulas might say, hey, your common sense stinks, and that's frequent in science, so we don't want to do that. What we do want to do is ask, what does it mean for this graph to end where this graph begins? Why? That's limits, right? So in order to show that it's continuous like this, we would need to show, and I expect you to do this when you do this, yes, that the left-hand limit, let's see, I need little r and then big R minus like that of G. We can call it little g of R if you like. Is supposed to be equal to the right-hand limit. That's little r is a little bit bigger than the surface of the Earth, like that. This is little g of R like that. And that's supposed to be what you get when you plug in the surface of the Earth and calculate the gravity. Now, in order to finish, you need to do two things. You need to calculate that limit using these formulas, calculate this limit using these formulas, plug in the number, make sure that this is true. Once this is true, and I look at this graph, it's now easy as pie to answer the question, when is this function continuous, and when is this function differentiable? All right, good luck.